Threats running beyond HTTP and cloud workloads. Let's start by talking about the evolving threat landscape. In recent times, the shift towards cloud-based and Linux-based environments has brought new challenges to the forefront. Protecting applications solely at the edge is no longer enough. Threats can emerge within running applications and APIs, outbound and egress traffic, and even within in-network east to west traffic. Over the past year, we've witnessed the world grapple with attempts to mitigate world-known breaches, such as Log4Shell, Spring4Shell, and Text4Shell. Many organizations struggle to handle these complex incidents and tackle them within runtime environments despite the existing runtime security products in market. Runtime threats have been a long-standing concern in the cybersecurity community, but traditional runtime protection approaches have been far from perfect. For example, RASP, or Runtime Application Self-Protection, has required the deployment of agents for every component within the tech stack, leading to deployment and maintenance challenges, with agents actively imposing CPU load and impacting application performance, as well as increasing operational costs. So why eBPF-based security? To address these evolving threats, we recently announced a new solution, Runtime API and Application Protection, designed to safeguard your workloads at runtime. In order to overcome the historical limitations of RASP solutions, ThreatX Runtime Protection leverages a technology called Extended Berkeley Packet Filter, or eBPF, a powerful framework that attaches to the kernel level within Linux environments. eBPF allows us to achieve real-time visibility into application processes and network traffic and protect runtime environments without modifying kernel code, granting insight into system components and activities beyond HTTP traffic. It enables us to monitor network flows, process tables, environment variables, and so much more. Unlike other methods, eBPF allows us to peer into kernel-level data without risking the integrity of the OS and enables ThreatX runtime protection to extend risk-based blocking to runtime environments, protect against threats including runtime threats, malware, and malicious rootkits, block high-risk transactions such as data exfiltration attempts or excessive data exposure, and detect and track threats across cloud-native and multi-cloud infrastructure. ThreatX Runtime API and Application Protection is the first cloud-native solution to detect and block runtime threats to APIs and applications. Its patent-pending capability leverages eBPF to extend protection to the runtime environment and deliver real-time blocking for runtime threats. The ThreatX Wrap solution is easily deployed as a sidecar container within a Kubernetes environment. Leveraging the eBPF technology, ThreatX Wrap enables deep network flow and system call inspection, process context tracing, and advanced data collection, profiling, and analytics. Powered by eBPF, ThreatX Wrap inspects network traffic anywhere on a host or node without requiring an inline deployment. ThreatX Wrap may be deployed as a standalone solution to address runtime environments or be coupled with ThreatX's API and Application Protection Edge solution for 360-degree ability to detect, track, and block threats to APIs and applications. ThreatX's Runtime dashboard provides a comprehensive system overview of your runtime environment. The timeline provides an overview of all historic event activity with the ability to distinguish between various classifications and apply filtering based on application, commands, tag classifications, rule sets, and risk. Rules can be also customized to detect and block specific events based on an organization's security requirements. With this toolset, security analysts can quickly stop threats and identify risk, malicious or anomalous events for further investigation. Let's start by using ThreatX's system browser in the Runtime dashboard to observe all runtime traffic and suspicious events being detected by ThreatX's WRAP sensor. Users can drill into high-risk events running on their workloads by using the dashboard's Miller column filtering to quickly and easily begin investigation. Now that we're looking at all high-risk traffic, users can drill down into even more specific classification or rule details. Classifications is based on the MITRE framework for identifying attacker behavior. ThreatX rules capture specific traffic patterns and behaviors, and each rule is aligned to a specific classification. For this use case, let's go ahead and dive into the command injection activity being detected by ThreatX's Runtime dashboard. Here, we can see all of the matching criteria for each event running on your applications. Now that we've selected command injection, we can see that there are two commands that are being picked up by ThreatX that are considered command injection: mount and whoim. Let's start by investigating the volume enumeration event with the mount command. The mount command allows users to mount or attach additional child file systems to a particular mount point on a currently accessible file system. The command passes the mount instructions to the kernel, which completes the operations. Attackers can use the mount command to mount a malicious payload to a file system to attack workloads. This is used, for example, when plugging in a USB to take over a machine. Now that we've drilled into this current event's details, we can see what specific rules have triggered this event by looking at the trigger conditions on the upper right-hand side. We can see both rules were detected for command injection as well as volume enumeration, with combination with the current timestamp and IDs for the process and UID and GUID. If we look above, we can see the timeline of how many times mount was used, as well as when it was actually executed upon as well. But the big question to answer is, where did this process come from? This is where we can start to use ThreatX's process graph. This will help security analysts pinpoint which application this command came from and when it was executed. Security teams can gain the visibility needed to begin triaging and continue locking down this application to prevent further spread of any malware that was attached using the mount command. Also, within the current event details, security analysts can understand specific environment variables so they can further triage what systems were potentially infected. This is just one example of how ThreatX's Runtime dashboard can help security teams identify high-risk traffic and begin to investigate runtime activity that could potentially be putting your workloads at risk. Jumping back to ThreatX's system browser, now we can start to look at more specific malicious commands that are being executed within runtime environments. Let's start to drill down into anomalous traffic that's trying to enumerate through all of the available directories and files running on this given workload. We can do this by filtering the commands by the ls command. The ls command is a Linux command used to list file directories, and this can be used from an attacker's perspective to identify valuable files that contain sensitive information or rewrite file permissions for ransomware attacks. The timeline view at the top of the system browser also reflects when and where this command has been executed, how many times, and will help security analysts understand the context needed around if this is malicious or anomalous behavior. Let's begin investigating this event by drilling into the specific details around the trigger conditions, again identifying which rule ThreatX matched this behavior against, the timestamp, And we can also see more context around the actual command line attempt that was executed on this Apache 2 application. To answer the $1,000,000 question as to where this command came from, we can again use the process graph below. Security analysts can use ThreatX's process graph to tell a more cohesive story about other commands that were being executed alongside this ls command. For example, if we highlight the netstat node, we can start to look at the specific information around the netstat command being used by attackers to potentially see network connections and understand where they can spread the next attack to. By understanding the process's child nodes and child commands together, ThreatX can help security analysts piece together a more cohesive story around the commands that are being used to take over this cloud workload and execute a more cohesive attack. Now that we can confirm that there's malicious traffic indicative of an attack by investigating further into this ls command, by seeing all the relevant events, security teams can begin triage and locking down this application as well. These were just a few examples of how ThreatX's runtime protection dashboard can help your team to identify and observe evolving runtime threats in your environment. Now we're going to hop into our Q&A session to get your questions answered by our cybersecurity experts, Alex Gatz, a senior security researcher here at ThreatX, and senior product manager, Tyler Hill.
Hey, good morning, Sydney.
Good morning, Alex, Tyler. Thanks so much for joining us for this event's live Q&A. We really appreciate both of you taking the time to join us. To really open up the conversation.
Thanks so much.
Yeah, of course, anytime. To really help us open up the conversation, Alex, I'm hoping that you could begin by helping to explain to the audience the backstory around how ThreatX's runtime capabilities really expand the original platform offering.
Yeah, absolutely. So historically, we had pretty strictly focused on edge protection. So expanding capabilities by like advanced TLS fingerprinting, building out various analyzers, really just trying to hyper focus on ensuring nothing makes it through the edge that shouldn't be. With Log4j, we kind of found that was extremely difficult when there's really easy ways to obfuscate payloads and really like rotate through a bunch of permutations of that obfuscation. So that kind of drove us to want to look into other methods of, I don't know, really like identifying what the payloads are actually doing and kind of just getting a more clear picture of what's happening on the application host itself or like within the application. This led us down a path towards eBPF technology, where we found that it was really easy to get a clear view of what's happening in the application and on the host itself. So that's kind of what drove us down this path, I guess.
Perfect. Thanks so much for kind of starting us off the conversation of really how this capability started to evolve and really some of the research that you've done on the cybersecurity side of things and how that impacted that decision. So thank you. Tyler, I want to switch this also to the product side. Can you walk us through kind of the decision-making process when deciding to pursue building runtime capabilities for ThreatX?
Yeah, absolutely, Sid. Two kind of key trends I would highlight that you touched upon in the presentation. Number one, the proliferation of cloud adoption. By no means anything new, but as that continues to saturate in the market, these attacks are becoming more at the forefront. And we see the trends of those types of runtime attacks emerging, whether it's a log4j or a log4shell. A lot of great examples that you called out there that a lot of organizations are really struggling to address. And whether it's in the form of visibility or more proactive protections to be able to stop those threats, that's exactly what we're trying to solve. And as we talk to customers, these types of things are really a big blind spot right now in terms of being able to see what's going on within a workload, being able to take proactive measures to not only identify those things, but stop them in their tracks. And so where we see, the general trend of the market going is as more customers adopt cloud or other cloud native technologies, having that visibility and awareness into workloads is critical for both meeting business and security requirements. And that was really the big thinking and strategy behind building out a cloud native runtime protection solution. So we're thrilled about the capabilities that this adds to the platform, and really being able to help our customers solve some of their toughest problems out here when it comes to security at runtime.
Great. Thanks so much, Tyler. And I think that's probably a truth for a lot of people who are tuning in to this event is, getting a more consolidated and cohesive view of exactly what is happening needs to go beyond just HTTP analytics at this point. So I do want to take a quick minute to shout out. This is a live Q&A for any folks who are joining us. Please feel free to post your own questions in the Q&A. We'll make sure to ask Tyler and Alex them as soon as we see them pop up. But it looks like we have another really great question coming in. Tyler, Alex, this would be one for both of you, actually. Could you give our audience maybe one or two examples of runtime threats or examples of cyber criminals hijacking workloads for runtime attacks?
Absolutely, I'll take that one and jump in. There's certainly a lot of different attack vectors and attack strategies for how attackers can get into a workload, hide, do nefarious things, do malicious things. It feels like there's a number of different attack vectors that will pop up in the news. But a great example, one that I saw in the news just the other day, was basically an attacker had infiltrated somebody's Kubernetes cluster and ultimately installed kind of a backdoor to be able to actually hijack that cluster, leverage it for a crypto mining purpose. So if someone sees their AWS bill going through the roof and they're wondering why is that, it's basically because the resources in the cloud, CPU and otherwise, had been basically hijacked for nefarious purposes. And that really highlights that lack of visibility where attackers can get into your workload and you may or may not know it. It may not be evident right away. Maybe there are some signs, but there's many different other attack vectors like that without that integrity and fidelity of the workload, nefarious things could be going on in the background that you may or may not have any idea about. And so our solution really is designed to provide that kernel level visibility up through the tech stack to be able to see everything that's going on, whether it's anomalous or explicitly malicious. We're able to categorize that, classify that based on the different types of commands, different patterns that are being detected within there. So again, that's one of many examples I could offer up personally, but that's ultimately how our solution is designed to provide our customers with that observability and detectability within the running aspect of the workload.
Great, and that's a great example. I think also to highlight that a lot of these cyber criminals, these threats, really are financially motivated at the end of the day. There's very few of them who have alternative reason to launch these really sophisticated attacks besides the financial aspect. Alex, I'm curious to jump over to your side as well. Any examples of runtime threats or attacks that you think could be interesting to share with our audience?
Yeah, I think some of the more interesting things that you can get a hold of with this technology is you can see if there's privilege escalations taking place. You can see if there's pivots from one container to another. You can see any attack that's happening across your traffic east to west. Whereas with an edge solution, we're really very limited to just that north-south traffic. So I think the horizon is very wide, and we have a lot of space that we can explore here with this technology.
Yeah, and Alex, I'm hoping that maybe we can jump in just a click further because I know that you led a lot of the research here at ThreatX around, how can we start to solve more specific problems for runtime threats and reviewing how a lot of RAS solutions have done this in the past. Would you mind just really high level explaining some of the main points that you found when doing that research?
Yeah, absolutely. So, many of the members of the audience here probably heard of RASP solutions. They were around for quite a while. I think some of the biggest reasons that they got shot down were one, because they were highly intrusive. It took a lot of effort to get them installed properly and to maintain these solutions. They introduced their own issues and they could introduce their own vulnerabilities. That was a big concern. And probably from the business perspective, I mean, it was a big cost, not just from a resource, not just from the personnel side, but also from resource utilization. So like your CPU utilization could double or triple, and I mean your RAM would skyrocket. So all of these issues kind of culminated into why I believe that RAS solutions never really fully took off like they could. It's not that they did a bad job; they did do a great job, but they had some pretty big pitfalls that were difficult to address at the time. And I guess I'll throw one more out there. The RAS solutions are really very limited into the context of information that they have access to. So they really are only looking at the application itself. They're not actually looking at like a holistic view. They're not looking at like what the host is doing beyond the application. They're not looking at what the entire environment is doing. So in a cloud deployment, like what's happening at the node level beyond just the host level, or even just beyond, the container, the host, whatever. So I think those were the biggest issues that I identified in my research around RASP solutions.
Great, and I really appreciate you sharing the depth that it really got into for evaluating the current problem state of the RASP solutions. How, it may have been a solution, but it was a solution that might have been hard to manage or taken a massive effort to roll out. And I think those are very real organizational changes that a lot of folks maybe don't want to recognize in hopes of finding some sort of solution. Um, Alex, I promise this is the one of the last times I'll pick on you. But I want to just flip this question on its head and ask you, when it came to evaluating eBPF, how did you find that it addressed some of the challenges in your RASP research?
Yeah, absolutely. So, um, for those of you not familiar with eBPF, it runs in essentially kind of like a VM running within the kernel itself. It has its own methods of verifying the bytecode that you're introducing to this VM, and it's very locked down. Like memory allocation is set up front. You're very restricted there. You can't go beyond those bounds. There's a lot of other protections that are in place, but I think the big things that differed from the typical RAS solutions were the resource utilization is amazing. I mean, the thing you're running this thing within the kernel. It's running essentially like with C code. It's running highly efficiently. Um, it runs very safely within the kernel. It's not intrusive at all. You're injecting this bytecode into the kernel that's then being verified, like I said before. So there are lots of checks in place that are making sure it's as secure and safe as possible. It's very far removed from any kind of kernel module or like custom kernel modification or anything remotely similar to that. You get direct access to raw streams of information. So you can get access in the network stack, for example. You can get a raw feed of information directly from the network driver if you want. Or you can kind of go a step above that and hook into what's called the traffic control, so like TC level. A step above that, you can get hold of XDP, and you can kind of keep moving through all of these different layers and decide where whatever solution you're trying to implement would be best suited to get that source of truth from. You can also get a hold of syscalls, so like entrances to the syscalls and exits from the syscalls, so you can see everything around what's happening with those various syscalls. And I guess like to explain what a syscall is, it's like a API between the kernel and your operating system. So the operating system makes calls down to the kernel. Syscalls are what the operating system uses to communicate with the kernel and send and receive information back and forth between the two. So your applications have to use syscalls at some point to do anything that they would want to do, like read or write or access files at all, or execute anything in a shell or anything like that. Those are all running through syscalls. I guess the other thing is RASP. I mentioned the context point about how RASP is very limited to the scope of the application itself. eBPF allows you to get a full view. So from the node level, all of the network traffic running through syscalls. You can even, if you really wanted to, which we don't actually do today, you can hook into the libraries that the application itself is using, and you can peer into that information and maybe identify anomalies that way. So it's really a holistic solution, and it's kind of amazing actually. I love eBPF.
That's great. And Alex, actually, we have another question coming from an audience member, and I think you just listed off some really great examples of what EVP does. But excuse me. But could you list off some examples of other application styles attacks EVPF can help with?
Oh yeah, absolutely. Arbitrary file reads and writes. I don't know. I mean, there's anything that you would try to trick an application into running. I guess part of this would be command injection, but anything else like pivots from the application to another source, installing shells, installing malware. Um, I guess just malware running on the system at all. Any kind of backdoors running at all, you can see really
Absolutely.
easily. Any anomalous network flow. So, like if a Docker container is trying to reach out to another Docker container when it doesn't normally do that. So, I guess like identifying any pivots that someone's trying to do. You can see any privilege escalations. You can see not just commands that are running through applications, so command injection, but you can see any commands that are running in the container at all. So if anybody found a way to pivot from one application to your application you're trying to protect, you can identify anything that's taking place that's anomalous that way. Um, I mean, countless things. BOLA, BFLA, you can get eyes into. Um, yeah, I mean, there's countless things. You almost have too much information to be honest. Like you really can get a hold of like everything.
Yeah, one other comment I'd chime in there too. Agnostic of the actual attack vector is a broader category. Just thinking about zero-day attacks, right? No matter how that attacker may be coming at you, they could be going after application vulnerabilities that may or not have been disclosed or even patched, for that matter. And having that visibility from the kernel level up allows us to see everything that could be happening. So exactly what Alex was talking about there. Hey, we've spotted something anomalous here. Something doesn't look quite right in terms of communication and east-west, or maybe there's data exfiltration happening in the environment. And being able to spot those 0 days, whether we know about them or not, gives us that visibility for, as a security team, hey, we can go and take action to shut this down and stop it. So, from a business perspective, I always like to think of that as the so what moment. Like, really, what does this provide? That full visibility to be able to see these types of emerging threats and have the visibility and actionability to go and stop them.
Yeah, absolutely.
Absolutely.
Yep. Yeah, I
Great.
could run with that a little bit if you don't mind.
Yeah, of course. Take it away, Alex.
So I gave the log4j example a while ago and how it's really easy to rotate through these various types of obfuscation. When you're looking at it from the eBPF level, you don't have to care about what the obfuscation technique is. Now you can just say, well, this application has never done this before. Why is it trying to do this now? You get a very clear and raw picture into what the system is doing itself versus trying to look at various payloads or various types of malware or anything that's being sent along via a payload. You don't have to care about that as much anymore. Now you have a clearly painted picture of what that payload was actually trying to do.
Great example.
Perfect. Now, I want to recognize we are coming up on our time today, but I wanted to ask Tyler one more question. I think I think it's common in the cybersecurity industry for the reuse and the recycle of various different terms and methodologies. Can you help just address the confusion between runtime protection versus runtime protection in multiple markets? We're hearing it in API as well as in the cloud native application workload market as well. Could you help just describe some of the differences between those two?
Sure. Well, when we talk about runtime protection, really the lens that I like to think about it is the operational aspect of your software or workloads when they're not at rest in the cloud. So an application is doing something, you have CPU utilization going on, you have, anything could be happening in a cloud environment, and really giving that full visibility into what's going on inside that workload is ultimately what we're solving here with this new solution. A lot of times you'll hear runtime protection tossed around loosely, thinking about, hey, we're just hitting your APIs, and what sort of visibility do you have at the gateway or beyond? And that's great. Absolutely need to have that sort of visibility. But what's actually happening inside once a request is processed, passed from the gateway and going into the tech stack to go in, process a resource, or go in, handle X number of commands, and really giving that holistic view of what's going on inside the workload is what we're aiming to solve here in a new and better way, leveraging eBPF as that core technology versus the RAS solutions of yesteryear that, as Alex pointed out, had leveraged a lot of the agent-based deployments to have to manually, manage those across your tech stack, and ultimately don't provide the full visibility. They also have, often had a lot of blind spots. So when we think about, runtime, that's what we're talking about here, that full visibility inside the workload that you can be running.
Perfect. Well, Tyler, Alex, I want to thank you both so much again for joining us for live Q&A today, answering some of our audience members' questions, and just helping to spread the understanding of how ThreatX provides runtime protection for APIs and applications. So thank you both so much.
Absolutely.
Awesome.
Thank you. Thanks for
Pleasure to be here. Thanks.
Perfect. Well, I want to thank everybody again for joining us today for the event on observing attacks beyond HTTP. We'll be giving away a select few attendees some ThreatX swag as a thank you to us. And we hope that you stay cool and enjoy the rest of your summer. Follow us on LinkedIn for future events. And thanks again.